Now we will learn in this series that how to find the number of subspace of a vector space. Okay, and how to find the number of linearly independent set of a vector space. Okay, so we will try to learn these concepts in which we will find that the cardinality of every finite field is of p to the power k, where k belongs to natural number and p is a prime. So we will prove first these statement, then we will learn about how to find the number of subspace, how to find the number of linearly independent set. Okay, these things. So first we will prove in this lecture that how every finite field has cardinality p to the power k, means prime to the power k, where k belongs to natural number. Okay, so let p be a characteristic of finite field. Okay, since field has cardinality finite, so every finite field has characteristic p prime. Okay, so this proof I will put in descriptions. Please watch if you do not know that every finite field has cardinal characteristic prime. Okay, since characteristic of a finite field is p, means that p dot 1 equal to 0. This will imply order of 1 is p. What does this mean by 1 plus 1 plus 1 dot dot plus 1 equal to 0? Means this is p times. Okay, so what we see that order of 1 is p. Order of 1 is p in F plus. What is the field? Definition of field, we will see in the ring theory that F plus be a abelian group. It is a abelian group, and F star dot is also an abelian group. Okay, so with respect to plus, it is a abelian group, and order of 1 is p. Okay, so in a group, what we know that order of any element divide order of group. So order of 1 is p, so order of element will divide order of field. Okay, this is the notation for cardinality of field. Now if possible, assume q is another factor of cardinality of field. Okay, we will prove that the cardinality of f is p to the power k. So if possible, we are assuming that cardinality of field is p to the power k, q to the power k1, k2, like this, and we will reach some uh, contradiction. Okay, and then we will prove that the cardinality of field is actually p to the power k. So where q is prime. Now since this is a factor, it will divide cardinality of field. Okay, then by Cauchy theorem for finite field, what we know that when a prime divide group, okay, when a prime divide cardinality of group or finite group, we have an element of that order in a group. So since q divide cardinality of f, so we have an element in the field such that order of x will be q. Okay, this is by Cauchy theorem for finite group. This will be group. Okay, we will learn in group theory course. Okay, so since order of x is q, means q dot x equal to 0, but also p dot x equal to 0. How? Because p dot x can be written as p dot 1 dot x, and it can be written as p dot 1 dot x, And what we know that p dot 1 equal to 0, because order of 1 is p and 0 dot x equal to 0, means what? P dot x equal to 0. Now p and q are relative primes, so we can find ab is in integer such that ap plus bq equal to 1. Okay, now ap plus bq dot x, so by distribution we can write here ap dot x plus bq dot x. Also we can write this as a dot a dot p dot x plus p dot q dot x. And what we know from here that p dot x equal to 0. Okay, so we can put here p dot x equal to 0 and q dot x is also 0 from here. Okay, so q dot x is also 0, means that a dot 0 plus b dot 0, and this is nothing but 0, and this is equal to 1, means 1 dot x equal to 0. Okay, because this is nothing but 1 and this dot x equal to 0 means 1 dot x equal to 0. But what we know that order of x is q prime, and prime has to be at least 2, but it says that order of x equal to less than equal to 1. This is not possible because we have assumed that q is a prime and order of x equal to q. This is a contradiction. Okay, so cardinality of f has no another prime factor. This means that cardinality of field is b to the power k, where k belongs to natural number. Okay, so thank you for watching this video and make sure please subscribe my channel. Okay, thank you.